Okay, so how do we minimize this? So when we talk about using the variational principle and minimizing something, we typically will impose some set of constraints and then use Lagrange multipliers in order to impose those constraints. So the constraint that we want is we need some normalization condition. And the reason that we need this is to avoid the trivial minimum, which is just that all the v's are 0. So we need a constraint which will allow us to avoid just getting back vi equals 0. So we can define a normalization that at some time t naught, the v's are normalized in this way. And therefore, we can't get v equals 0 as a solution. So I'll talk about a little bit where t naught comes from. It's similar to like in matrix prony, where you were writing down recursion relations for correlation functions at different times, and you needed to think about which time slices you might include in that. And that will also be one of your questions later. But let's go ahead and get to solving this. So we can impose this constraint with a Lagrange multiplier. And so the thing that we want to minimize, this function lambda, so this is the thing that we're trying to minimize, and then we need a Lagrange multiplier lambda to impose our constraint. Hopefully you can still read this. I'm running out of space. Oh, whoops, hang on. All right, I'm gonna write it below. That's not fitting. Okay. So this is our Lagrange multiplier, and then we have our normalization condition. And we want to impose that this part is equal to 1, so this whole thing is 0 with this Lagrange multiplier. And when you do this, so in order to minimize this, we're going to differentiate with respect to our v's, because that's the thing that we want to vary. And that's pretty simple to do. And so in the end, what you get is the following. Okay, so I've now suppressed the indices. So the C is a matrix with indices suppressed. V is a vector. Lambda now depends on t, because you'll have a different value for lambda depending on what value of t you have in here. And then we have our matrix C of t naught times v. And this is a generalized eigenvalue problem. It looks very similar to the one that we had with matrix prony, except now instead of having vectors C is a matrix. And in particular, it's a positive definite matrix. So as I said, for a positive definite matrix, the eigenvalues are positive. which is good because we're talking about a variational principle here. And when you talk about a variational principle and you talk about minimizing something, you need to know whether the function is positive or negative, because you can't minimize a negative function. And so the variational principle will find a minimum for a given energy level. So we already talked about positive, definite, well, we talked about correlation functions, and if they have all positive overlaps, that's another way of saying it's a positive definite correlation function. And then we said that if you looked at the effective mass versus time, it would always approach the ground state from above. And so that's what the variational principle is kind of taking advantage of. The fact that we're trying to minimize the correlation function down to some given energy level. All right, I will go ahead and pause that. You have one more question here.